हेलो ठीक है. Very good morning. Yeah, today is the 4th day. Let me first of all wish all the lady candidates happy Women's Day. Okay, we already have learned quite a bit about the interior of the earth from the xenolith perspective basically. So there is bound to be little repetition because I'm going to show you something from the Indian perspective, and then we will move on to basically the ecologites, which we have not touched upon. Okay, so initial this thing is going to be little repetition. We all know that earth has a layered structure. It has been divisible into 3 different shells: the core, mantle and the crust. And the 2 remaining spheres, basically the lithospheres, atmosphere, biosphere and hydrosphere, basically all are part and parcel of the planet Earth. And this is the only dynamic planet, since it has basically, I would say, heat inside, and therefore to a great extent to run this machinery or engine you require to have some fuel. That fuel is basically the heat. Heat carries all sorts of movement, in the sense the convection currents, the lithospheric plates move here and there, and so on and so forth. Okay, so these are some of the features basically of the planet Earth. And the thickness, the crust base generally have 6 to 35 kilometer thickness. It is smaller in case of the oceanic crust. It is larger in case of the continental crust. Oceanic crust being denser, it gets subducted, and therefore after its formation of the mid-oceanic ridges, it is destined to get destroyed, and therefore generally we do not have any oceanic crust older than Jurassic. It's all throughout has been consumed. Against that, the continental crust is lighter, generally made up of felsic minerals, and therefore the density is low. It floats and it keeps on accumulating. So throughout the geological time scale, the thickness has increased. That's the reason we have some of the oldest rocks as old as 3.5 billion years old, or there are some zircons, detrital zircons, which are as old as 3.7, 3.8 billion years old. So basically the continental crust gets preserved, against which in contrast basically the oceanic crust gets destroyed as such. And in the core, we know basically the outer core is liquid, whereas the inner core is more solid in character as such. These are some of the other characteristic features or the different, I would say, elements of hydrosphere, crust, mantle, core, and the thickness, volume, density, mass %. I will not get into those details. This is what is the general picture that generally we all know as we start moving towards the interior. Per kilometer of distance that you travel down, there is a increase in temperature of the order of 35 degrees centigrade, and then the pressure also starts operating upon. As the thickness of the overburden goes on increasing, the thickness and when the thickness goes on increasing, obviously the pressure also goes on increasing, and therefore these are 2 important parameters while melting any solid material from the earth, the temperature and pressure. And the third element that we have looked at basically is the volatile content, which to an extent yesterday Michel has talked about, wherein the fluid transport that takes place is through the volatile content, and through the fluid basically there is elemental transfer also happens, causing enrichment or depletion processes, what we call as metasomatism. So all these 3 variables have an important role to play as long as basically the igneous activity is on, and depending upon the variation in these parameters, the melting of the mantle happens as such. These are the 10 major elements that we normally speak of, and their distribution mostly in the whole earth and in the earth's crust as such. You can see basically that iron is dominant 35% in the whole earth. In the earth crust basically, if you look at, The silicon content is higher, 28%, and the rest all elements to a great extent are generally lower in content as such. But you can see the potassium content, the sodium content generally is much higher in the earth crust, which is to an extent diminishing or lower when we compare it with the whole earth as such. Okay. When we speak about the earth's interior, the proxies that we make use of, or the material that is available to study the earth interior, basically that we have seen the Amphibolite suit or Amphibolite complex. I will be speaking about it maybe day after tomorrow, wherein we will try looking at the different various parameters and the characteristic feature the Amphibolite complexes associated with the Himalayan belt as such. And wherein we all know the Amphibolites are basically the slivers or pieces of the oceanic crust which have escaped subduction. So instead of going down, they have slide past and gone onto the adjoining continental region. So especially in the orogenic region, you have such slivers preserved, and they give us an opportunity to study the oceanic crust and the residual mantle, the leftover portion of the mantle at the base as such. Okay. So the Amphibolite suit is important from the point of view of understanding of the Earth's interior, and we will be paying some attention to it. With respect to the changing depth and pressure, normally we also get to see mineralogical transformations happening as such. We all know for sure that the mantle is periodic in composition and basically ultramafic in nature. The MgO content is very high, and as the depth increases, the four mineral that makes up mostly the peridotite keeps on changing, or rather they get transformed into a new species which is more stable to the changed temperature pressure condition. So in the upper 410 kilometers, basically at that depth, olivine gets converted into spinel, which is generally a low velocity layer. Transition zone, as velocity increases rapidly, then at 660 kilometers seismic discontinuity, the spinel gets converted into perovskite type, and then generally at the lower mantle, which the velocity changes very gradually as such. We have looked into basically what are the mineral transformation that take place, ferropericlase or woostite or ringwoodite, and many more mineral species that we have spoken of, generally which occur as inclusions within the diamonds, and from that we understand what is the phase transformation that is happening and at what depth and at what temperature. So both the pressure and temperature gets constrained on the basis of these various different mineral species, and generally the four mineral sort of a composition eventually reduced down to almost two minerals, and that is happens at much greater depths as such. I will skip some of these slides. Composition of mantle, thickest layer, generally the mass wise distribution is 64% of mass is constituted or made up of your mantle, which has generally a thickness of 2900 kilometers. It is made of iron and magnesium, allows the tectonic plates to move. Convection happens here. As we all know, as we start moving in, the temperature goes on increasing, and the heat to a great extent is responsible for the convection current to operate, and based on basically this, the plates move in different direction. And we all know there are three different types of basically plate movement that we speak of: convergent margins, divergent margins, and the third being basically where the plates grind past each other, like the San Andreas fault. That's a best example. Almost all magmas and all metamorphic rocks are generated in interior of planets, and our attempt is basically need to know the composition, structure, temperature, pressure, and rheological state, whether it is a solid phase, whether it is a liquid phase, or a mixture of solid and liquid, what we call is a mushy, at different depths, at different locations, especially at different tectonic settings. And that is the reason we normally look at the four kinds of basalt: the continental flat basalt, the island arc basalt, then the ocean island basalt, and the mid-ocean ridge basalt, all of them belonging basically to four different tectonic settings where different sort of a mantle dynamics and mantle process are operating, and they are giving rise to the chemistry that we get to see, which is very different in all the 4 types of basalts as such. Okay. So what are the data that we have to understand the Earth's interior? So first of all, the most common is the drilling process, through which you can recover the samples. But again, we have some limitations that we can maximum go down to a depth of around 12 kilometers. The example time again I keep on giving is the Kola Peninsula of Russia, where the first deepest drilling activity took place, and we have a complete core of 12 kilometer depth. Incidentally, I keep on also mentioning about a similar activity that is presently happening in India at Koina, and wherein we are going down to a depth of 8 kilometers. So far we have drilled 16 exploratory wells of the depth varying between say around 1.2 to 3 kilometers. So what is beneath the Deccan Trap, that is basically we are trying to look at. And similarly, what is the thermal structure, what is the fluid basically that is getting transported, what are the causes of seismicity in that particular region, whether fluid is playing an important role or something else is happening, so and so and so forth. So various different parameters to a great extent can be studied with this deepest drilling program, what is called a deep, that is happening at Koina. And we haven't been to Koina, but perhaps maybe this semester or next semester we'll try to make a trip to. Okay. Then next is the indirect means through which we can make the understanding this geophysics, which include basically the seismic surveys, the gravity surveys, the magnetics or magnetic studies, and the heat flow measurement that we generally make, which to an extent gives indirect understanding about the nature of that particular region. So high heat flow, low heat flow. Generally low heat flow is more commonly seen in colder regions, which are the cratonic regions, which are the stabilized regions. So tectonically active regions will have generally higher heat flow as compared to tectonically very stable regions like the cratonic regions. So the Himalayan part, if you measure the heat flow, they are going to be distinctly different than the heat flow that we have in the Karnataka region, especially in the peninsular shield region as such. Then the xenoliths, there are 3 kinds of xenoliths that we have looked at, coming from the various different depths. The other day he was mentioning about some of the xenoliths all the way coming from a depth of 660 kilometers, that is the seismic discontinuity that we speak of. But generally the deepest xenoliths commonly been recovered are of the order of or of the depth of 250 kilometers. There are also xenoliths coming from shallow depths, especially the Kutch region, from where we have recovered and studied some xenoliths. They are coming from almost a crust mantle boundary, 40 to 45 kilometers, not more than that. Apart from that, basically there are kimberlites and lamproids to a great extent bringing up xenoliths of deeper origin, which generally of the order of 250 kilometers depth as such, which to an extent contain mostly garnet, and we all know garnet is stable beyond 90 kilometers. So the kimberlites and the lamproitic magmas obviously must be having a deeper source of generation, or the source must be located at great depths, and after its melting, when they start moving up, since they are volatilely charged, the volatile content is higher, so basically the movement or speed with which this magma ascent or move upward is much faster. So without undergoing any equilibration basically with the country rock or the wall rock, whatever that come in its way, it's brought to the surface. So xenoliths are basically accidentally caught up fragments of the Earth's interior. And when we speak about the spinel larzolite or the garnet harzburgite, there are 3rd kinds of xenoliths that we normally get commonly are the crustal rocks or deeper crustal materials, like the crustal xenolith that commonly been seen in tholeitic basaltic dikes. In India, basically I have already given an example. They are coming mostly from the Narmada sector. In the Narmada region, the Nandurbar region, there are a couple of dikes which are xenolithic in character, but those xenoliths are mostly of crustal materials. So granites, granodiorites, quartz veins, or sometimes BI, banded magnetite or banded hematite quartzite, shell, limestone, sandstones, all those materials been brought to the surface as such. So those are also equally important because that gives us an understanding about the deeper part of the continental crust. What is the composition of the continental crust? So that's the reason we generally divide the continental crust into upper continental crust and lower continental crust based on its composition as well. Then deeply eroded continents, the best example basically the granulite that we speak of or look at from the southern granulite terrain of India, and the idea being basically whatever was overlying is been eroded away. So the root zones are exposed. So whatever was on top, that top part, the lid part is to a great extent removed through the erosional process, and therefore the root zones are exposed. So the granulite to a great extent makes up the lower part of the lower crust as such. There are mafic granulite, there are felsic granulite, so there are debates always goes on which is the actual correct sample of the lower part of the earth crust as such, but there are certain xenoliths of granulite been recovered from the lamprophyre dikes which are occurring to the south of Mumbai in the Murud-Jinjira region, and which to an extent seems to have been actually more mafic composition as such. So those probably representing to a great extent the deeper portion of the continental crust. Okay, and sometime if you go further deep, perhaps you would be getting into the eclogite phases as such. So these kind of materials to a great extent are used as proxies in understanding the Earth's interior. Ophiolite complex I already have mentioned about. The meteorites, what are they? Michel has given you the understanding and insight into the various different kinds of meteorites, and they are to a great extent are again differentiated one, or sometimes they are very primitive one based on which may make use of their composition for our studies, keeping them or considering them as proxies representing basically the composition of the solar system as such. And therefore most of our comparison that we make, especially in igneous petrology, are to those rocks, the meteorites, mostly the chondrites basically, to which we make the comparison. And the last mode of basically understanding the Earth's interior is the theoretical and lab models. So the experimental petrology, wherein you try simulating the natural conditions in the laboratory. I must have spoken about that. It began in the Canberra, Australian National University, where Grin and Ringwood performed the initial experiment, and there are good papers that are available how to generate the basaltic magma from a source material, what temperature, pressure conditions are required, and similar kind of labs are also present in Japan. For example, Yoder or Kushiro, those publications, formation of basaltic magma are wonderful sort of a piece of material or literature which to a great extent gives an understanding about how to basically how the three various variables that we speak of, temperature, pressure, and to a great extent volatile content, control the magmatic process or control the magma generation as such. So those are the other sort of sources from where we can understand about the Earth's interior as such. So the most commonly studied are the xenoliths, and I already have mentioned about there are crustal xenoliths, and there are I would say mantle xenoliths. The mineralogy to a great extent help us in understanding about the temperature pressure conditions, and overall basically the composition tells us about whether we are looking at a depleted mantle or an enriched mantle, and so on and so forth. So the metasomatic process in great detail has been getting discussed over here. In fact, till date I was speaking about only two types of metasomatism, the cryptic and modal, but you've been introduced to the third category, and that is given by basically Sue and Bill Griffin from the GEOMOC, that is the Macquarie University, Australia, wherein we have seen a new addition basically of clinopyroxenes. So there is no new exotic mineral species that is getting formed, but a new mineral of the same mineralogy, in the sense clinopyroxene, orthopyroxene, olivine. In that basically the clinopyroxene to a great extent would be added further by the metasomatic process, and that is the third metasomatic process that we have understood so far. So the mantle xenoliths, this picture even was shown by Michel. So they are smaller in size, mostly green in color. The green color is due to the chrome dioxide. Chromium to a great extent impart green color to the clinopyroxene. So they are easy to actually recognize in the field. Generally been seen present among the alkaline magmatic rocks like the nephelonites, besonite, melanephelonites, lamprophytes, kimberlites, lamproids, alkali olivine basalt. They are not commonly seen in tholeiitic rocks because tholeiitic magmas generally those magma get stored somewhere beneath the crust in the magma chambers, and therefore there is a more time made available, and even if it carries something, it perhaps would get dissolved into it. So that is the case with tholeiitic magmas. So tholeiitic magmas or basalt do not carry any mantle xenoliths. Possibly they to an extent can carry definitely the crustal xenoliths depending upon the force with which the magma has emplaced as such. Okay. So these are some of the dikes which are hosting xenoliths coming from the Kutch region as such. There are alkali olivine dikes, olivine basaltic dikes or melanephylitic dikes, and they have been seen emplaced in variety of rock types. For example, in this particular case you can see they are emplaced in the limestones also. Okay. So many times you can have those alteration zones along the marginal part, vertical distribution. Sometimes there are even sills been reported from the Kutch region, and sills to a great extent speaks of magmatic underplating as such. So depending upon the nature, this is another basically a lamproid that has been seen present on the surface. Here you can see this is a dike of lamproid, but incidentally it doesn't carry any mantle xenoliths as such. There is a size variation with respect to the mantle xenoliths. You can see it can be of a boulder size, the entire thing is of peridotite, or it could be little smaller than that, but generally the size is very small as such. I visited couple of places, especially in the African part and in the Yemen region, especially the Atak region, wherein we could recover this big size of a mantle xenolith. But unfortunately, both whatever area that we have in India, whether it is Kutch or whether it is basically the lamprophyte dikes that are exposed to the south of Bombay, they generally carry xenoliths of very small size, 1.5 or sometimes less than that centimeter size sort of a xenoliths been recovered, and that to a great extent basically puts a limitation how to study those xenoliths, how to basically carry out the chemistry. Incidentally, there are good techniques that are made available. The laser ablation ICP-MS to a great extent through which it is possible to actually have an in situ analysis of the minerals that are present, and that is how we have progressed further in even working on a very small material of a very small size. Otherwise previously it used to be a difficult task as such. So these are the xenoliths that I am showing you coming from the Kutch region, and you can to an extent understand the size. This is a small size of a xenolith. These are generally honey yellow and granular in nature. The color basically is due to it has been exposed to the climate or the atmosphere, and because of which it is highly altered. It since is dominated by basically olivine bearing material, or olivine is a dominant mineral, and therefore olivine is very prone to alteration. So many a times you can have this kind of a color, and the size, as I mentioned, about 2 to 5 centimeters. They are subangular to angular in nature, and this is how they look under the microscope as such. Okay. You can see this reddish brown thing is the spinel, and spinel in fact has a variety of forms and shapes. To a great extent, the morphology of the spinel actually has been considered as sort of an indicator of the stress conditions. So there is a French group basically which have worked on the stress regime, just studying the mantle xenoliths and especially concentrating on the morphology of spinels, the holy leaf shape, the elongated shape occurring as idiomorphic grain inside the clinopyroxene, outside the clinopyroxene, based on which you can understand basically what is the stress regime, the pressure at which basically these materials have moved, and that to great extent actually changes the morphology as well as to great extent even the composition. Many a time it has been seen the aluminous spinel, initially aluminous in character, rich in alumina content, eventually gets converted into more chromium rich spinel as such. So all those permutations and combinations been studied by many people. Here you can see in fact it is outlining the orthopyroxene and just getting sort of enveloping the clinopyroxene, orthopyroxene as such. Here you can see yesterday he was mentioning about the alkali magmas to a great extent can react with the mantle xenoliths, and they can be a very I would say a very potential candidates of mantle metasomatism. Here you can see this kind of a reaction ream that is getting developed as this particular magma is getting infiltrated into the mantle xenolith as such. So all these minute observations generally gives you an understanding of the various different processes that are operating at great depths. This is another important picture, and from our study from Kutch region as such. It was a publication that we made in Current Science, and here you can see it to a great extent. These needle like material that you are looking at, basically those are all rutiles, and those rutiles occurring as more or less exsolution features or as inclusions in many of the clinopyroxenes as such. And so to an extent it is a very enigmatic thing, and therefore such kind of a material to a great extent can be considered as a product of mantle metasomatic process as such. So this is a physical evidence that you have. These are all rutile inclusions, and to a great extent these rutile occur as inclusion mostly in the clinopyroxenes along with spinel. You can have even reddish brown color material. This is basically a spinel. So that speaks of basically the metasomatic activity the mantle in this part of earth, especially in the Kutch region, have undergone as such. Okay, so there are also you have to be very careful while observing these various xenoliths as such. Then generally based on the xenoliths, based on their chemistry to a great extent, you can understand about how much amount of melting the original source material must have undergone to give this particular residue which we have picked up as the mantle xenoliths as such. So that to an extent can be worked out on the basis of basically the chemistry. There are some famous diagram that we can make use of, and based on which to an extent we can understand about how much amount of partial melting the original source material must have undergone so as to produce the present mantle xenolith or the present mantle mineralogy as such. So this is a graph, basically the CR number of spinel upon Mg number. Mg number is a differentiation index, Mg plus 2 Mg2 plus upon Mg plus Fe plus 2 into 100. That is the Mg number, and this is the CR number, CR upon Cr2O3 plus Al2O3. Okay, so that is been considered, and based on which you can see in fact these are the model lines. You can start from 1% to 10% to 15, 20, 25, 30%. All our Kutch xenoliths actually occupy this particular region between 1 to 10%. So the amount of partial melting the source material, the source mantle must have undergone is in the tune of about 1 to 10% as such. Okay. There are crustal xenoliths bearing dike commonly seen in the Kutch, in the Nandurbar region of the Narmada sector as such, and they provide unequivocal evidence for the presence of heterogeneous basement through which this basaltic material must have emplaced as such. So the crustal xenolith bearing dikes so far reported are from the Narmada Tapi tectonic zone and the west coast region, implying that basically you understand about the nature of the basement, how heterogeneous it is in character. Generally when we speak of basement we always talk in terms of gneissic basement as such, but there are some other materials also which can be part of the basement as such, and our understanding about the basement can come through basically through these various studies as such. So this is the picture to a great extent. This is the dike that you get to see at a place called Ranala, which is a small village close to Nandurbar. And this particular dike you can see, in fact, it is a hillock running for almost 60 kilometers in length, and the width could be of the order of 50 to 100 meters. So such giant dikes one can see over there, and to a great extent many of them shows presence of such material. These are the crustal materials, the crustal xenoliths, and in fact you can spend almost a week's time measuring their size as well as the composition as such, and based on which you can have the frequency distribution diagram that to an extent will give you an understanding of what is the dominant lithology. For example, over here in a small say work of almost 1.5 to 2 days, we could get gneiss species 119 in numbers, which corresponds to almost 50.6% of the basement material, vein quartz 18.3%, granite 10.6%, granite myelonite 7.6%, and rest all goes on diminishing. Banded quartzites also were reported as a xenolith material from these dikes as such. And this is under microscope that you can understand that how the magma gets contaminated when it reacts with basically the crystal material. So these are some of the textural aspects that you can study, and you can see to a great extent basically the quartz grains of the gneissic basement are getting diffused and getting to an extent mobilized, or rather get melted and get mixed up with the magma. And that is what we have been generally in case of Deccan that we speak of when we look at the Deccan stratigraphy as such. Generally there are 11 formations to which we classify the basalts to, and of those 11 formations, the lowermost formations are the most contaminated one. So there is a physical evidence as well as the chemical evidence that you can have, and whether it has interacted with the crustal gradient or the lithospheric gradient, that is the upper mantle, all those features to a great extent can be picked up on the basis of basically the chemistry as such. So this is what we normally look at. Then next important sort of a material that is coming from or coming as xenolithic material are the eclogites as such. And the eclogites, you all know, generally are of high pressure, ultra high pressure basically materials, wherein a normal basaltic rock to a great extent get converted if it is buried to great depth into an eclogite. So under high pressure there is a complete transformation of a basaltic material into an eclogite, and during that particular mineralogical transformation basically the physical attributes such as density also goes on increasing, and sometimes that is the reason why generally when the oceanic slab gets subducted, we to a great extent are through the various different methods able to trace the journey. It has been seen it is going to a depth of 660 kilometers. Beyond that basically we do not understand much about what is happening to this. But if you remember, I must have spoken about the D dash layer just after the outer core, which is the liquid core, and wherein it is generally believed that the oceanic slab later on been converted into eclogite, and because of the higher density those eclogite masses all the way can sink down all the way throughout the mantle material and can get deposited at the core mantle boundary as such, and that's how the D dash layer gets created as such. So there are various different sort of theories and speculations people make of. Generally when we speak of eclogites, there are two kinds of, as Michel was telling you, that we are very generally fond of making classifications. So here also you have a classification in case of eclogite, generally orogenic eclogites, and you have what are called as anorogenic eclogites as such. So those which are formed through the transformation or burial of oceanic slab to deeper levels in a subduction zone environment, there also the basaltic material or the mid-ocean ridge basalt gets converted into an eclogite. And the other way you can generate eclogite, the magma to a great extent which are generated at deeper levels, but they do not come to the surface and get crystallized there at a crust mantle interface or at great depths as such, what is called as isobaric cooling. cooling that is happening at a high pressure as such. There also you can have a generation of eclogites, and those eclogites are commonly seen as been entrained mostly into the kimberlites or the lamproids. Kimberlites and lamproids to a great extent have So basically you have two kinds of eclogites, the one which are cooled at greater depths, that is the magma cooled at greater depths, that is called as isobaric cooling. There you can have conversion of the basaltic magma into eclogites, and those generally are picked up by the kimberlitic magma. So in kimberlites you can have all possibilities of getting eclogites as xenoliths, the garnet Harzburgite as xenoliths, spinolarzolites as xenoliths, as well as the crystalline materials. So those are the best sort of a candidates to look for the interior material as such, and that is what commonly been studied as such. The other way basically where the oceanic crust is consumed or been buried to deeper levels through the process of subduction, and there also possibly the crust to a great extent can get transformed into the eclogites, and during the exhumation process basically the material, the continental crust to a great extent is comparatively lighter, and therefore it is more buoyant. So even if you to a great extent pull it inside beyond a particular depth, it will not go, it will start its journey upward as such, and depending upon the exhumation rate, the rise with which the continental crust has come up, it to an extent would decide those sort of a metamorphosed material whether to get them retained with respect to the mineralogy or not. So if the exhumation rates are higher, it is an accidental sort of a case wherein the eclogites would get preserved, but generally otherwise it is a progressive metamorphism that has happened. So if it is coming up, there has to be retrogression, so there has to be a retrograde metamorphism also happening, but sometimes the exhumation rates are so high, so it doesn't allow the retrogression to take place. Instead, whatever the original mineralogy to a great extent is retained, and they are brought to the surface as such. And this is what is the case of the xenoliths or the enclaves of eclogite that you get to see occurring in some of the gneissic materials coming from basically the Somorari complex along the Indus-Sangpo suture zone in the Himalayan region as such. So these are called as ultra high pressure belts in the Himalaya as such. Okay, and this was established with the discovery of the mineral coesite from Somorari, India by Sachan in 2001, and from the Kagan Valley of Pakistan basically. The eclogites from the area occur as lenses or irregular bodies within the basement and cover gneiss and are strongly overprinted by Amphibolite facies assemblages. So many of them are retrogressed, but few of them are retained as eclogites. Okay. Preservation of high pressure minerals, for example coesite, stishovite and coesite, these are the ultra high pressure polymorph of silica as such, and generally the stishovite are more commonly seen in areas where is a meteorite impact. Generally the areas like the famous case that we have, the Lonar crater coming from the Buldana districts of Maharashtra, wherein it is believed that the crater has been created due to the meteorite impact as such. Incidentally and unfortunately, we have not reported or come across any stishovite mineral, and therefore there is always sort of a debate that goes on whether it is a volcanic crater or a crater created by a meteorite impacted. The rest all the basically properties are there. The suevitic ring, which is basically a brecciated material along the margin, the striation that you get to see on the walls of that crater as such. So there are many evidences in favor, but mineralogically there are none as such, and therefore there is always that debate that goes on. We have not been not have reached to any consensus how this particular crater may have been created as such. Okay. So there is the common mineral reported is stishovite, whereas coesite is commonly been seen present as inclusions, especially within the garnets coming from basically eclogites as such. Okay. So this is basically the picture of a small outcrop that is exposed, and this is the Pagar gneiss, and you can see very well over here. These are the enclave, the lensoidal sort of a material which is distinctly different in color from a distance only. On the basis of the tone of the color you can make out this is a different material, and these are the pieces of the same material been actually rolled down. You can in fact collect these materials and can look at, but all of them are not eclogite. There are many such lenses, almost more than 100, but very few of them actually reported to be eclogites. Rest all are turned out to be amphibolites as such. Okay. This is what is the retrogressed eclogite. This is more of an amphibolite as such, full of garnet, without any coesite, without basically the characteristic soda-rich clinopyroxene in the amphasite, that is not been seen present, which is the characteristic mineral of the eclogites as such. Okay. So coesites and the amphasite, that to an extent basically are the most characteristic or diagnostic minerals of the eclogites, which are seen missing over here. Rest all mostly the amphiboles, and to a great extent what you have are actually the garnets. So when we look at the petrography as such, the major mineral assemblage is garnet, clinopyroxene, which to an extent a soda-rich clinopyroxene, which is an amphasite. Then phengite. Phengite is again a mica, which is generally formed at a very high pressure as such. Okay. Then you have cave feldspar, amphiboles, zoesites, fen, rutile, quartz. So variety of minerals, but majority of them, these ones are occurring as accessory phases as such. And herein you can see to a great extent a small inclusion, which to an extent the colorless material over here, and this is actually is a coesite, and to a great extent you can see the radial cracks that are developed when this particular mineral got trapped into the garnet structure as such. So basically these are some of the petrographic evidences or mineralogical evidences to call it as an eclogite. So the theory is the continental slab which was pulled in and got buried to a great depth of 100 kilometers. From there it got converted, the basaltic material got converted into eclogite, and then it started exhuming up, and perhaps the exhumation rates or the upliftment was so faster that it could not get re-equilibrated or could not get retrogressed to, and that is how the original mineralogy is preserved as such. Okay. Rest of the minerals that include basically are, you can see garnet and the amphibole. These are the clinopyroxene, which are to an extent the amphasites, and this is the coesite that you get to see. Many times even the coesite is also altered. So garnet occur as large idioblastic whole porphyroblasts ranging in size from 0.5 to 1.5 millimeter in size, and exhibit intense optical zoning from reddish core to pale mantle and rims as such. So in fact they are idiomorphic, very octa euhedral in shape as such, and to a great extent in fact those are called as basically we'll get into those are called atoll garnets, wherein sometimes the core and then between the core and the margin you can have the development of phengite mica. So these are some of basically the characteristic features. Garnet cores are distinctly rich in Ca and Fe, basically surrounded by thick Mg rich rims. The grossular content decreases and the pyrope content increases sharply from core to rim. So even the composition is not homogeneous. You can get to see a change in its Mg content from core to the margin as such. So that's the compositionally zoned garnets. Common inclusions in the garnet core consist of bluish green amphiboles, phengite and epidote, that is zoesite, while the rim shows presence of pale colored amphasite and rutile. Amphasite mainly occur as unadult or subadult pale green colored grains restricted to the matrix. Amphasites are strongly zoned with a jadeite content, and the acmite content basically 35 to 42. Cores where the rims are relatively lower in jadeite. Rims of the most amphibole granite exhibit symplectite intergrowth of clinopyroxene with feldspar, whereas the cores are occupied by exsolution lamellae. It's basically the soda content. The plagioclase, to a great extent, if get buried to deeper level, the soda that is released is get converted into what is called as amphibole or soda-rich clinopyroxene. So the same when is brought to the surface, if there is a sort of equilibration that takes place and the exhumation rates are lower, perhaps it would get converted back into plagioclase feldspar. So this is what the mineralogical transformation that one can study while studying the eclogites. So amphiboles from TMC can be classified into two types: pre-eclogitic and post-eclogitic. Those formed because of the burial of the crust, and prior to that those were present as such. Okay, so those both things to a great extent can be studied. So these are some of the sort of inferences drawn on the basis of basically the textural studies. Fangites are also most abundant mineral phases constituting the atoll structure, and these are the atoll garnets that you can get to see. Okay, and these are the various different minerals that one can see over here. So biotite, hornblende, then you have amphibole, garnet. This is the fangite mica. Perhaps few more pictures here. You can see a very euhedral outline, sort of a garnet, and this is a garnet core. It's called as the Garnet Island to a great extent, and which is surrounded by this basically the yellowish color that you are looking at is actually a fangite mica as such. And to a great extent the development of atoll structures, again from that we to an extent can understand what are the geological processes that have operated upon as such. So these are various different pictures. In fact, there are various different sort of stages of the atoll structure development as such, and this has been depicted through these photomicrographs A, B, C, D, E, F, and you can see in fact this is how perhaps the beginning of the formation of the atoll structure must have started, and this is the end of it, where you can get a complete sort of the island, the inside island to a great extent is completely dissolved, and these are the various different stages of atoll garnet developments as such. Now how this particular development has occurred, whether it is fluid aided or whether it is temperature dependent, pressure dependent, what is the mechanism of atoll formation, that needs to be again understood, and that is what Malika did during her dissertation, the PhD dissertation, and that is how basically. So we did couple of things basically. Herein you can to a great extent see the images, the electron images basically of these various different atoll structures as such, and to a great extent simultaneously the chemistry to an extent was understood or rather measured, and you can, in fact you can see from core to the margin rim to the core how the mineral how basically the chemical content goes on changing as such. So here you can have look at basically the Mn content and the Mg content perhaps, and from core to margin you can have such sort of a change in its the content of these various different elements as such. So these are some of the images based on which basically a sort of a traversing was done, and the chemistry to a great extent with the help of basically probe, the chemistry to an extent was understood, and the plotting was done so as to understand basically what is the exact mechanism of to a great extent the formation of the atoll structures as such. Then these are the symplectite intergrowths, the plagioclase feldspar on the amphibole basically, or amphiboles and plagioclase, various different sort of a textural aspect that to an extent are essential. As I said, without doing basically the petrography, to an extent you will not come to basically the exact mechanism by which the petrogenesis of these rock formations. So it is very essential to actually look at the mineralogy under microscope. Some of very beautiful pictures of the symplectite intergrowths. This is the mineral chemistry based on which to a great extent the classification is done, especially with respect to these are what? Clinopyroxene amphibolite. Malika kidhar hai? Anyway, okay, the various different minerals, basically ferropergasite. These are the amphibole classification to a great extent. This particular one basically is giving you a classification of the clinopyroxene. All of them are getting plotted into the amphicite. Here this is for the amphibole. You have different varieties of amphibole: ferropergasite, termite, can't make out, ferroketophonite, ketophorite, winkite, and so on and so forth. So the various different mineral species been classified on the basis of the chemistry, which is otherwise the optical, they are so small, so with respect to the optical properties, it is not possible to classify them. So we are making use of the chemistry in classifying those different varieties. Then the whole rock geochemistry to a great extent was undertaken, so wherein they were crushed to powders, and basically the major oxide content as well as the trace element and RE content to a great extent were measured. And this particular chemistry to a great extent is of use in classifying those rocks. You can see they to a great extent getting classified into what are called as a subalkaline basalts as such, and this is basically the Mg number versus the rest of the transitional metals like chromium, nickel, and cobalt, and their plotting based on which to an extent you can deduce certain assumptions, certain sort of inferences. Here you can do the classification, and to a great extent you can also understand about the tectonic setting within which this rock must have occurred. So basically more of a mob setting, and then whether the mob is of P type, N type, or E type, then what is the setting, basically MORB or OIB. So the tectonic setting to a great extent can be understood on the basis of plotting of this data. So trace element behavior during retrogression, so that is also you can see as we started getting uplifted, what are the elemental transfer or elemental changes that have occurred. So the chemistry is a robust tool in understanding these various different stages of exhumation also, as well as the atoll formation, and this is what has been done as such. Okay, so basically large and lithophile element, you can see big spikes for them. Then first series transitional metals, immobile elements, and rare earth element. Basically in the atoll formation, with respect to the retrogression and with respect to the burial, what elemental transformation that has occurred to an extent can be studied making use of the chemistry. So elemental abundances of HFSC, niobium, tantalum, zirconium, titanium are observed to plot near or close to 0, representing no gain or loss from the system during retrogression. Elemental concentration of large and lithophile elements like K, RB, CS, and Ba show pronounced enrichment, more than almost 250%. Strontium depletions are most pronounced in the retrograde sample, suggesting high immobility during retrogression. Among the transitional metal, chromium, nickel, and copper show moderate to prominent enrichment, ranging from 120 to 300% in the retrograde sample. Positive correlation between chromium with that of Mg and Ni suggests that Mg and Ni have undergone relative enrichment during retrogression, and Cr enrichment shows no correlation when plotted against LiLe. Cr when plotted against Pb shows a negative correlation. So basically all these plots to great extent suggest what elements are added and what elements have left the system as such. So how the enrichment has occurred and how basically the depletion has occurred, and to a great extent based on this particular chemistry you to an extent infer about what is the fluid basically that may have played an important role in making the atoll structure, in bringing those samples from deeper level to shallower depth as such. So all those permutation combinations been worked out. So multi-element spiderograms been plotted. Here you can see them. These are basically the graphs, mostly the RE patterns, and here the multi-elemental patterns, and you can see they are more comparable to EMORP. So basically in enriched kind of a mid-ocean rich basalt been to an extent been buried to and been transformed into eclogates, and then you can make comparison with basically what is the geology of the Indian continental margin that went subduction as such. So what is that particular part which was basaltic in composition that has been transformed into eclogite? So to a great extent you can speak about the protolith. So here in this particular case, this is still in a realm of speculation. We to an extent believe that mostly the Permian basalts, basically the Panjal troughs, which to an extent were part of the Indian continental margin, which got subducted, buried to, and been transformed to eclogite. So the protolith for those eclogite looks to be the Panjal troughs or some materials of the Panjal troughs which has been subducted as such. Okay. As you can also to a great extent find out the temperature pressure condition, and this is what the geothermometry and geobarometry, and you to a great extent in this particular diagram also understand about basically the path during which this complete sort of a conversion of a normal garnet into an atoll structure that have taken place. So this is what one can do, making study of the petrography, the geochemistry, the stress elemental behavior, the temperature pressure conditions, and to an extent you can hypothesize basically how the transformation may have occurred as such. Okay. So conclusions, this is the last part. Formation of whole garnets. Mineral chemistry and petrography show that the eclogite do not represent a single equilibrium assemblage. Whole garnets have highest Ca and Mn concentration and lowest Mg, indicating early nucleation and well-defined prograde zonation pattern with an increase in pyrope and decrease in grossular and spacetine content. Inclusions of soda and calcium amphibole, zoisite, rutile, magnetite within the garnet cores represent the pre-UHP stage resulting from metamorphism of mafic protolith and constitute the first preserved prograde association of minerals. Presence of amphicite and coescent inclusions at the garnet outer rim define the UHP stage evident by highest Mg toward the garnet rims, and calculated temperature basically 462 to 508 degrees centigrade for garnet cores and 768 degrees centigrade for garnet rims, with highest Mg and phengite with the highest Si content are consistent with garnet growth during subduction. So basically how this particular transformation of a normal garnet or a normal sort of a basaltic protolith that has been converted into an eclogite, and within the eclogite basically how the garnets are converted into an atoll structure. So all those things to an extent can be deduced on the basis of basically these various different parameters. So this is the sort of paragenesis of the atoll garnet formation, and I will not get into details of these. The ophiolite part that I will try to cover perhaps during the next lecture. Thank you so very much. Any questions? If there are no questions, Michel will take the dais. Pardon?
Is retrogression is related with metamorphic rock? If it is, then why not for?
Why not for igneous? Means when the magma is moving up? कारण प्रोग्रेशन बरियल जेव्हा होतं ना, सगळं जे आहे ते सॉलिड फेज ट्रान्सफॉर्मेशन आहे. मॅग्मामध्ये इग्नियसमध्ये सगळं मॅग्मॅटिक म्हणजे फ्लुइड आलं त्याच्यामध्ये. त्याच्या कुठे ते वर येत नाहीत नॉर्मली, ते वरचं सगळं इरोड झालेलं आहे, त्यामुळे दे आर एक्सपोज. दे डोंट ऑन देअर ओन डोंट कम. इफ दे कम ऑब्वियसली दे विल अंडरगो रेट्रोग्रेशन. ओके. Yeah, no problem. Yeah. Yes. Pardon? Both the pressure and temperature will go on changing. again relatively they are speaking, granulite is also high pressure, eclogite is a high pressure, but relatively again the pressure content is variable as such. So when it is coming up, so basically zeolite facies, then you have greenish facies, then you have amphibolite facies, they have bluish facies, there would be a in between a granulite facies and the eclogite. When you start reversing it, from eclogite it will come to what? Either to granulite or bluish, and the characteristic mineral basically would tell you which is the exact facies to which it is getting transferred to. So when you speak about the basically bluish metamorphism, the glaucophene basically. So if the glaucophene is present, so there is a conversion that is happening during retrogression when it is coming up. Okay.
Ça leur va. Ça leur va. Non, mais j'ai dit à Malika, j'ai même à un moment demandé, pratiquement voulu demander si on pouvait rentrer le mardi soir. J'ai dit, mais bon, après j'ai calculé que si j'étais vendredi au labo pour la thèse, ça allait, mais il faut absolument que j'y sois parce qu'il soutient le mardi. Oui, mais ça on peut voir. Après, c'est que Raymond, il nous a dit, ce qu'on peut faire, c'est que moi comme je l'ai dit, j'ai dit, moi il y a un jour où je peux te laisser de la place parce que bah, les comatis, je peux les faire, les pyroxénites, on en a parlé plein. Écoute, à la limite, s'il faut en faire une petite mardi, on en fera une petite mardi, mais après on arrête. Hein. Sorry to speak in French with the micro. So you are ready to deal again with the metasomatism? As you understand, I am a lover of metasomatism. I like the mantle metasomatism. So today, I will in fact do my first part will focus on the second main type of metasomatism we have in the mantle xenolith from phanerozoic mantle, what I call the mantle wedge or the hydrous metasomatism, the one with orthopyroxene, with a small comparison with the things we saw yesterday for Kerguelen, because it's two very different settings. Intraplate oceanic setting for Kerguelen, you remember, and this one is a substrate subduction zone setting. And after, I will show you what we did also on some mantle metasomatism beneath the Cap Val Craton. So we are going back in time to Archean mantle and to see what happened in some of the samples from this mantle. Okay? So I will start with Island of Lear. It's a job I did during my postdoc with Professor Susan Oreilly, you know the name, no, from GEMOC in Australia. And with a colleague, he was at the CSIRO in Sydney at that time, Brent McInnes. Now he moved to Perth. He's the head of a department of Perth, but he moved also to more Genesis processes and this kind of stuff. But at this time, he contacted Sue and me because they find nice xenoliths. Sorry, because it's all presentation. I was young and I did some effect, but I know I don't know the way to to put this effect down. So, location. Just here, this place is near Papua New Guinea. You know, Australia is here, Papua New Guinea. And this is a place we call New Ireland. This is close to the Manus Trench, where the Ontong Java Plateau, the largest oceanic plateau in the world, much larger than the Kerguelen one, is blocked in the subduction. It's blocking the subduction, in fact. You have the trench, and the plateau is here, like a big piece, and it blocks the subduction. So we are in a four-arc basin, subduction setting. And a German vessel, don't ask me the name, I don't remember, it's a German name, complicated for French also to remember. So they did dredging in the sea, and we were very lucky, because at what time, when they dredge from 1,000 meters depth, they have fresh mantle xenolith from under the sea. Look, this is not the sample you expect from under the sea. Under the sea, when you have peridotite, abyssal peridotite, they are well serpentinized. But this one, look, they look like the xenolith we have at the surface in a basalt. They are green, because they are made mostly of olivine, orthopyroxene, clinopyroxene, and spinel. Okay? That means that probably the eruption of this xenolith were a short time before the vessel came, in fact. Because you don't keep this kind of fresh sample in the sea for a long time. So probably a very actual recent eruption bring this mantle, this sample from the mantle in the spinel stability field to the surface at the bottom of the sea. So we were very lucky. But of course, you understand, if you compare this dredging with the map I showed you yesterday on Kerguelen, 100 kilometers north-south, east-west, with a lot of localities, much less sample because we have only one locality in this case. So you see the size, 12.8 centimeter. It's one of the largest. In place, the host rocks is a kind of high alkaline melt, high potassic. It's a kind of shoshonite, something like this, because it's a very strange area for magmatism. But you know, when you look in the end sample like this, the previous one was a typical peridotite, homogeneous. But if you look in detail, well, you forget this fracture. It's a leg fracture. But here, you see something. So you see a vein like this going on, and some small one here. And if you look in detail under the microscope, and don't forget the basic thing for petrologists are the microscope. Everything you do after, you do well if you did a very good petrographic study before. You have to know very well your sample, especially when your samples are complicated. So what we see here, it's a vein, and this vein is with oxide and a lot of fibrous mineral. At the beginning, we were surprised. It was in 2001, because nobody in the literature described this at that time. And of course, we went to the electron microprobe because we tried with a microscope. But in fact, it was simply orthopyroxene. But not the same orthopyroxene we have in the peridotite host rock. You know, it's all these fibrous crystals are orthopyroxene. It was strange, and sometimes they look very nice. Look, it's not the texture we expect from orthopyroxene when we are a guy working on the mantle. This is why we were very surprised at the beginning. All these nice textures are orthopyroxene. And the main mineral from this vein are orthopyroxene. So let's go to the microprobe, second step after the microscope. So here it's, if I remember well, sorry for the slide, I think it's calcium against aluminium. And you see the difference of composition between the primary clinopyroxene we have in host rocks, close to the vein. It's a typical mantle here, mantle clinopyroxene. And the one with the orthopyroxene, because we have a little bit of clinopyroxene with the orthopyroxene inside the vein, are quite different in composition. The same for orthopyroxene, aluminium against calcium. Very nice difference of composition between the primary orthopyroxene, the big one, coarse grain one, more than 5 millimeter in size, and the very teeny fibrous one here, very low in aluminium, and in calcium. Look at this one. So after third step of petrologists like me working on Mantle Xenoliths, after the microprobe, I'm going to the laser to have the trace element content in orthopyroxene. Okay, paragenesis texture the microscope, a major element composition in mineral. We go to the probe, and after for the trace element, we go to the laser ablation ICP-MS. So here for the primary orthopyroxene, you can see I already told you 2 days ago, this kind of rare element pattern for orthopyroxene and even for clinopyroxene, we always interpret the same way. We explain by a 2-step processes with first a partial melting event, giving you this general shape here with a decreasing of light rare earth element over heavy rare earth element. But you see here for the lanthanum, the most incompatible rare earth element, you start to have an increase. This is an evidence that you start to have a metasomatic processes. The same for the what we call the extended pattern, because we add other trace element to rare earth element, and we have some typical anomaly, like here anomaly in uranium. Forget the lead, because in fact we find the positive lead anomaly in almost all the pyroxene we analyze in Xenoliths. Titanium also. So this is a typical pattern we find in the primary orthopyroxene in the sample from Lille. And after the clinopyroxene, in the primary clinopyroxene is the same sample. So you have the tendency to have the same kind of pattern. You know, sometimes you have almost no effect of metasomatism. Here, you have almost a pure pattern after partial melting. But so probably we have some evidence that some of the part of the upper mantle beneath this part of the world was not affected by the metasomatism. And they tell us a story before the metasomatic event. A partial melting, and you know, when we have the use of this kind of pattern, is not a low partial melting degree. When you have, you know, this depletion in lateral of element, you are between 5 and 10% of partial melting. So it starts to be a very high degree of melting. At 10-15%, you do the morb. So typically tolelite are more than 10% of partial melting of the mantle. Alkaline melt are close to 1, 2, 3%. High alkaline melt are less than 1% of partial melting, and carbonatitic is 0.01%. Well, of course, you need to have a slightly different mantle, but mostly is this. So here, almost pure residue after partial melting, but some other sample, you know, the clinopyroxene, you can see the same evolution than in orthopyroxene, big depletion, and after you start to re-enrich lanthanum and cerium. Same kind of anomaly than we see with orthopyroxene. It's a diagram normalized to primitive mantle. We have to notice this enrichment in uranium, especially a high uranium-thorium ratio, and we don't see this kind of enrichment of uranium in intraplaque setting. It's the first difference with the typical alkaline metasomatism we showed yesterday in Kerguelen. We were lucky because in the vein, I show you, we have, I told you we have some clinopyroxenes, new clinopyroxene, not the same as the primary one, and they are big enough to do laser. Because it's easy to do electron microprobe, because you have a very small spot, typically 1 micrometer in cubic meter. You understand? Very small one, and for the laser spot, it's 50 micrometer. Below this, now with the new laser, femtos gone, we start to go down to 10, 20. But to work at that time, it was in 2000, because we published in 2001. Yes, typical good size was between 50 and 100 micrometer size. Okay, so we were lucky. The orthopyroxene and clinopyroxene, even the fibrous orthopyroxene, were big enough to be analyzed with the laser. And there are very nice patterns, see, for the trace element, still normalized to primitive mantle, with huge anomaly in niobium. Huge anomaly here in zirconium, huge in titanium. Okay? And if you remember your all the lessons you had about magmatism in the past, these kind of fixtures are typical of arc magma, andesite, and one of the characteristics of the melt, the magma in subduction setting, in this negative anomaly in what we call HFSE, niobium, tantalum, zirconium, hafnium, and titanium. So you look, even in clinopyroxene, orthopyroxene, of course, the concentration is always higher in clinopyroxene because they like trace element more than orthopyroxene, just because they have a different crystalline structure. So it's easier to put trace element in the clinopyroxene. We have to remember that they are incompatible elements. What they prefer first is a melt, but some part of them are going inside the mineral. Okay, but more in clinopyroxene than on orthopyroxene. This is why, during a long time, it was almost impossible to analyze by laser the trace element in orthopyroxene. With the new machine coming, the new ICP-MS, the new laser, we have new method, and now we are able to do rare earth element and even other incompatible trace element directly in orthopyroxene. It's very interesting because the future is this. Because clinopyroxene is not a main phase in the mantle. It's always between, let's say, a few percent to maximum 15%. Most of the mantle, the peridotite, now you understand, is olivine. So olivine is still a big challenge to analyze by laser. We have method, thanks to Mathieu, to separate olivine in the lab, and we can do rare earth element by solution, but you don't have the textural relationship. For orthopyroxene, no, we can directly on thick section. You know, it's a thin section, but a little bit thicker, 100 micron thick. You can analyze directly the orthopyroxene for this, and it's very interesting. And we were the first one to do this, but we were lucky also because for orthopyroxene they are not typical. Mathieu yesterday told you that typically orthopyroxene have pattern like this, you see? But these fibrous orthopyroxene are very different from the typical mantle one. You see this kind of pattern, and a similar pattern to clinopyroxene. And we have also in this vein few crystals of biotite, phlogopite, and few crystals of amphibole. And look at the pattern. And in fact, before this kind of study, people were analyzed phlogopite and amphibole in the mantle xenolith. And the typical idea, it was a good idea because they did a good analysis, is this kind of mineral can concentrate the niobium, tantalum, titanium. But you can see here, they also have no enrichment in this element. They are able to take this element, but they don't have inside. Why? Because the melt, which form these two minerals, were just with no HFSE. If you have no niobium inside the melt, even if you have a mineral it lacks the niobium, you will have no niobium in your mineral because you have no niobium. And this is, we were very surprised by this result because even the mineral they like this kind of element, they are very poor in this element. It was a good information for the nature of the melt. So after that, we conclude history, because we are geologists, so we like to tell history about the Earth. In this part of the world, first, high degree of partial melting, and probably linked to a mid-ocean ridge center. Remember, we estimate at 10% the degree of melting, was probably to form stolitic basalt. And after, modal metasomatism, predominance of orthopyroxene is the metasomatic paragenesis. Major and trace element of mineral, we have the presence of, I forgot, we have a lot of water-rich inclusion in this fibrous orthopyroxene. A good indicator for the nature of the melt. Fibrous habit of orthopyroxene and the lack of shear structure in the vein indicate that the metasomatic event which affect this previously depleted mantle is recent and probably occur because also you can keep this kind of fibrous texture for a long time inside the mantle. So it was probably an event just before the eruption. Is recent and probably occur via hydraulic fracturing. You remember this kind of vein we have, caused by the influx of slab-derived iderous silica-rich fluid. Silica-rich because orthopyroxene is a phase with around 55 to 56% of silica. It's more rich in silica than a peridotite, than an olivine. Trace element of metasomatic orthopyroxene, climbyroxene, amphibole, and phlogopite indicate that the slab-derived fluid are poor in HFSE, typical feature of subduction zone. And we conclude that the preferential melting of this kind of region, metasomatize this kind of fluid of melt, could account for the HFSE anomaly observed in the arc prolated lava. Probably the lava with this kind of anomaly in HFSE come from the melting of this kind of mantle. When this mantle is going down, and because you have this kind of event in the lower part of the spinel facies in the mantle, but you know it's a dynamic subduction dynamic. If you put this peridotite at higher temperature, you melt, you will form probably arc magma with this characteristic. So a short comparison between the two types from yesterday and from today, just to remember you, it's important because after we generalize this comparison, and in fact it worked for a lot of locality in the world. For the Kerguelen, you remember a lot of different metasomatic paragenesis. The main one with new clinopyroxene, phlogopite, amphibole, or we have amphibole, ilmenite, phlogopite. I don't want to go in detail, but a very large diversity of metasomatic paragenesis because, of course, we have a lot of samples, a lot of localities, and here, one man with one very big difference with Kerguelen is the predominance of orthopyroxene, with a little bit of new olivine, clinopyroxene, phlogopite, amphibole, and sulfide and magnetite. If we compare the primary clinopyroxene, sorry for the slide, for what we call the cryptic metasomatism. I told you yesterday, this morning, we have this different type of metasomatism. This one, remember, it just you have no new exotic phase from metasomatic agent, only chemical modification. So we compare the clinopyroxene from Kerguelen, the clinopyroxene from Lihir, and you see we don't have to go in much detail, but they don't display the same anomaly, and especially they don't display with this thorium and uranium special feature, and they are not so depleted in HFSE. Okay, so not the same chemical modification. So now the secondary clinopyroxene, so we can tell now the still metasomatism because it's a new clinopyroxene, it's not the primary one. Sorry, this one is very bad, but it's a very old one. But just, we don't have this big HFSE anomaly here, and still you can see this thorium-uranium feature in here, and even with a lot more sample, we never find this kind of feature in Kerguelen. So very different metasomatic agent. Phlogopite, because you remember we have also very different. Look, especially if you look niobium here, titanium, HFSE, enriched in Kerguelen, because the metasomatic agent is alkaline, is rich in HFSE, so you can put HFSE inside the phlogopite. Here, for Lihir, nothing. Okay, it's a very important feature because you know the importance of HFSE in order to distinguish different kind of magmatism, and especially the intraplaque magmatism versus the suprasubduction magmatism. Mantle, coming from the mantle. I'm not talking about crystal study. So maybe if you have question, because now I will switch to other study I did before also, but this study we are going in time. We are going to the Archean mantle and to see what we can see in this mantle peridotite. But I think I repeat a lot about these two kinds of metasomatism. It should be a little bit clear. You don't have to understand everything. You have to remember that in Phanerozoic mantle xenolith, we have two main types of paragenesis because we have two main types of metasomatic agents. And of course, because we are in two different geodynamic settings, intraplate versus suprasubduction zone. But sometimes in suprasubduction zone, we find also some kind of metasomatism similar to what we find in intraplaque setting, because subduction zones are very complex, and sometimes if you have a slab break-off and you have a upwelling of your asthenosphere, you will have alkaline magma, and if you have alkaline magma coming in the mantle, they can metasomatize your mantle and form the same paragenesis as the paragenesis we have in Kerguelen. But it works for the intraplaque versus suprasubduction zone, and of course, as all classification, in detail, we can show some difference. So you are ready to go to new metasomatic assemblage? Or we can have the question at the end. We will see also clinopyroxene and phlogopite, and not the same, but okay. So now we are moving to the study we did about mafic and ultramafic xenolith from the Cap Val Craton. It's a craton from South Africa. And the title of the project was 12 element evidence for mantle magmatic and metasomatic processes associated to the kimberlitic magmatism. You know the host rocks is mostly kimberlite in the case of Craton. We observe that two kinds of xenolith-bearing kimberlitic rocks are present. No, it's a general introduction. In fact, we have two main types of kimberlite in the world. What we call the group 1 kimberlite. And in South Africa, they erupt in at least 5 episodes in Southern Africa from 1,600 million years to 50 million years. And we find also orangeite. It's also the same name of group 2 kimberlite, or some people, they give the name Micaceus kimberlite. And they are almost unique. At that time, early 2000, they were unique, but now somebody finds some orangeite in other cratons. But they are very rare. The most important group of kimberlite is this one. You can find in the Siberian Craton, you can find in the Cabal Craton, in the Slav Craton in Canada. And so these ones are almost unique to South Africa and appear to derive from the lithospheric mantle, and this one from the asthenospheric mantle, but I have a second slide. Mostly the difference can occur in isotopic composition. Here epsilon neodymium, now you are pro of this, after the talk of Mathieu, against strontium isotopic ratio. So just show you, because I am not an isotopist, I am sure that the data are good, and after I can interpret the data. This is my job. So it's simple today, two groups. You see, here the kimberlite from the group 1, the kimberlite from the group 2. One example for group 1, one example of group 2, much more mica inside, the micaceous kimberlite. So for people, specialists of kimberlite, group 1 are asthenospheric derived. Okay? They have signature close to one of the actual OIB. Okay? For this one, it's more complicated, and in fact, they derive from the partial melting of lithospheric source, plus or minus metasomatized. No, it's not the same source. But this is just for information, because what I am a specialist of is more this, you know. You see this example of kimberlite with a lot of xenoliths inside, and they have also a lot of xenocryst, you know, monomineral xenolith with a lot of phlogopite, but a lot of garnet, zircon. It's a garbage kimberlite, because I told you that the speed is the speed of sound. You imagine the eruption at depth at 200, 250 kilometers. You have a big explosion. And in fact, you fragment a lot of the wall rocks and you put everything to the surface. You have also some crystal, of course, xenoliths. All the way, the kimberlite is fragmented everything. So let's go back to the mantle. Just this one, just to show you that there is a lot of kimberlite, you know, in the Cabal Craton, mostly located in South Africa. Kimberlite, you know, and you have some kimberlite. Why kimberlite were so studied? Because some of them have diamond inside. Okay. So one example of a mine, you know, it's closed now because it's full of water. It's one of the most famous mines of diamond in South Africa. It's a Kimberley mine in the Bultfontein area, in the center of South Africa. I told you 2 days ago, we are not talking about the same size here. You see the hammer here, and it's not a small one. It's a big hammer like this, and you see sometimes peridotite are quite big. I saw in their mantle room some garnet peridotite like this. Very impressed. And remember the density of this kind of rocks, 3.2, 3.4, you know, the energy you need for a kimberlite to put this one to the surface. And a lot of them. Because why? Because when they did the mining, they didn't care about the xenolith. They were looking for diamond. So when they mine, they put the xenolith away. You know, they form some dumps. And in fact, you had dumps of mantle xenolith. And for the geologists, when they came, in the last century, they were very happy because you have mountain of xenoliths and you have just to select the xenolith you want to study. No, it's finished now. Because after a while, the mining company, they discover that you have also diamond inside the xenolith. So they came back to the dumps, crush everything, you know, and now actually you have, in a lot of South African old diamond mine, you have no more samples. Everything was crushed to see if we have more diamond to sell after. But look, when I was a postdoc, I had a good friend. He's still working in South Africa, David Bell. And in fact, he took, he had some friend in the mining company, and they tell him, if you want more xenolith, it's the time to come now. So it was middle of around 95, 96, he came, he collected a lot of samples, trying to select the one we did not have the use in the past to study. And so up, this is why we have a nice collection, but everything now is crushed. But so remember, big size. But we have numerous types of mantle xenoliths applied by kimberlite. We have garnet and spinel peridotite, lerzolite, erzborgite, verlite, dunite. No, you know this nomenclature. Garnet bearing and garnet free pyroxenite, some websterite, clinopyroxenite, orthopyroxenite. We have phlogopite rich mafic xenolith. I will come back on this. Some eclogite, mantle eclogite and xenolith on this one. Megacryst, I will tell you, and a great number of big xenoliths display evidences of metasomatic reaction. The previous study before the one we did proposed a large panel of metasomatic agents with silicate melt, alkaline, basaltic, to kimberlitic, lamproitic, a lot of water-rich or methane-rich fluid. This was a story before. What we did with Dev, it was when I was a postdoc in Cape Town University, to test the various hypotheses regarding the nature of the mantle magmatic and metasomatic agent. And especially, we were looking to the kimberlitic nature of some of them. We have selected two different types of xenolith from the Caval Craton. Why? Because it's well exposed, large number of pipe and xenolith, and largely studied before. We selected the phlogopite-rich mafic xenolith, just to test this xenolith, because before there were a little bit of study, but the things were not so clear. I don't know if they are clear now, but I think, at least in my mind, they are clear. Garnet lerzolite with or without phlogopite and chromite. But we selected our sample, and they come from 4 major pipes. Kimberlitic pipe from South Africa, the Bulfontein one, the photo I show you, but also the Jagerfontein one, it's a very, very famous one, the Monastery one, all are old diamond mine, and this one is a premier mine north of Johannesburg, and this one, these are with kimberlite. The age of this eruption are between 120, 150 million years ago. But this one is a very old kimberlite. The age is 1.9 gigayear. So in fact, the information about this mantle is to be compared with this also. It's a very different age. So let's go back to the first type of xenolith we selected, phlogopite rich. And in fact, we have two types. We have what people call the married rocks, because it's rocks made of mica, phlogopite, amphibole, it's a special amphibole, potassic richterite, it's an orthoamphibole, in fact, it's not a clinoamphibole, rutile, ilmenite, diopside. And we give ourselves the name to another type of xenolith we call peak rocks, because they are different in mineralogy, because they have only phlogopite, ilmenite, and a clinopyroxene. Okay? So one example, they are very nice and very fresh. You see, the married one, phlogopite, mostly, and richterite with some rutile. And you have, when you are lucky, sometimes you have some clinopyroxene like this. Peak, phlogopite, very small clinopyroxene. Sometimes they are bigger, and big ilmenite. So two main types of what the hypothesis were probably these two kinds of rocks are cumulates of something, but cumulates or segregates of what? So still the same approach for a petrologist. We compare, we did the electron microprobe analysis, and you can see the difference in composition between the two types of mafic xenolith. Here it's for the major element in phlogopite and ilmenite. I think here it's for the ilmenite. You know, the ilmenite from the married are not the same than the mineral from the peak. It's the same for the phlogopite in a Mg number versus aluminium plot. You distinguish very well the peak field and the married field. So cumulate, but from two different origins. Up, let's go to the laser. I was lucky when I did my postdoc because at GMUG they had laser, and in Cape Town they have laser, so and microprobe. So I had my toys, and I could play a lot with. So clinopyroxene. You see also the trace element pattern in still the same kind of the diagram. Sample normalized to primitive mantle. You don't have to be a specialist to see that you have a difference. You only need eyes. You see, this one is not the same as this one, especially the scale is not the same. It's the same. Sometimes we play with the scale, but this one is the same. So, like the major element, same kind of conclusion. We have two different compositions for clinopyroxene. Sometimes petrology is very easy. It's not so complicated. For isotopes, epsilon neodymium against epsilon strontium, and our idea was to compare the isotopic composition from our xenolith to the isotopic composition for the two types of kimberlite, because we were looking to the relationship between kimberlite and the xenolith we have in the Cap Balcraton. And we were lucky. Look, for the married, they plot inside the field for the type 2 kimberlite. And for the peak here, they plot inside the field of type 1 kimberlite. You don't need big modelization at this time. You can just conclude that your peak, your rocks, your xenoliths, rich in phlogopite, are deep segregate from kimberlite, from type 1 kimberlite. And for the married, they are linked to the type 2 kimberlite. So we demonstrate that these two kinds of rare xenoliths were just deep product of the kimberlitic magmatism. So they are magmatic rocks, mantle segregate from high alkaline mafic silicate melt. It was the hypothesis at the beginning, and at the end we conclude, and we publish in a paper in 2002, I think, I remember, peak rock, group 1 kimberlitic melt cumulates, married rocks, group 2 kimberlitic melt cumulates, or sometimes product of reaction, complicated reaction, because people did more study after about married, and it's not so clear. It's a typical cumulates, but everybody, we all agree that they are product of the kimberlitic group 2 magmatism. But it's a little bit more complicated. Some people think they are not typical cumulates. They are probably product of reaction with previous peridotite, and you have big reaction and you form this married. But at this time, the link between the two types of kimberlite and the two types of xenolith is clear, and is still clear. So after that, we go to the main type of xenolith we have in Cap Val. They are garnet plus or minus phlogopite lersolite. So typical peridotite. We select coarse grain and deform xenolith, because there is two main types of peridotite inside the Cap Val Craton. What people they call low T, because its the temperature of calibration are relatively low. They come from a depth close to 100 to 150 kilometers. And high deformed porphyroclastic xenolith with high temperature of calibration, they probably come from the base of the craton, close to 200 kilometers. So we select like this, just to have a look at the mineralogy, the trace element, and the major element composition. They come from the same locality: Bullefontaine, Jagerfontaine, Monastery, and Premier. Some nice picture with garnet. And remember, most of the peridotite in kimberlite are garnet peridotite, because they come from very big depth, and they collect a lot at the beginning, a lot of garnet peridotite and less spinel peridotite after during the ascension. You see, it's very nice for a petrologist like me, because we like big minerals, especially for the laser ablation. You see the small spot of ablation here? We have clinopyroxene, garnet, olivine, and the orthopyroxene is somewhere else. And here is probably altered phlogopite. You see, they are not so fresh as the phanerosic xenolith from Kerguelen, for example, because they are much older also. But they are big and good for analysis. Sometimes the garnet display this kind of texture. They are corroded. They don't feel very well, and you have a corona here. It's a corona destabilization with the crystallization of some phlogopite. And this is typical, there is pyroxene around. This is typical of a reaction with the kimberlitic melt. This. A lot of people studied this one, this kind of texture. Nice peridotite, big garnet. You see the spot for the laser. You are able to do core and rim. And even if you want, you can do the in between the two. So it's not so common to have this kind of size. Nice orthopyroxene, olivine, and probably some clinopyroxene. You remember I told you that the specialists of kimberlitic xenoliths, they don't have the same nomenclature than us. For them, a lerzolite is when you have one crystal of clinopyroxene, is already a lerzolite. The international classification, remember, is modal abundance is 5%, limit between erzborgite and lerzolite for the clinopyroxene. But they work together for a very long time. So lerzolite, even if you have a teeny clinopyroxene wear, is not an erzborgite. So, but because we were looking for laser ablation, we selected the lerzolite. A very porphyroclastic one, high temperature garnet lerzolite, you see, with big garnet, and you have this matrix of olivine with porphyroclast of orthopyroxene here, and you have sometime also here. I think it's a very small clinopyroxene, but I am not sure. And sometimes some oxide, and you know the corona of destabilization of the garnet. You see the difference between the typical, what we call protogranular or coarse grain texture, and the porphyroclastic one. And big phlogopite sometimes, still with the laser spot. So, major element. And what we discover in our collection of garnet lerzolite from the Cap Val, we have also two types of clinopyroxene in composition. MG number against sodium, chromium, sodium. And you see, you have this tip 1, like this, and the tip 2. And they don't have the same composition. Same rocks, same texture. It's not depending on the texture. In the two groups, you have a porphyroclastic, a coarse grain. You have phlogopite or not. It's just a difference in the composition of the clinopyroxene. This one, some are very rich in MG number, and close to 95. And you know, this one are commonly higher in chromium, higher in sodium. So, trace element, not a pattern here, it's a ratio, you know, rare earth element ratio, samarium, ytterbium against cerium, ytterbium, lanthanum, niobium against, is not a rare earth, of course, against euryopum, titanium, lanthan, niobium against samarium, hafnium. And you can see, it's more clear than for the major element. You have these two groups, typical two groups of clinopyroxene. Under the microscope, they look the same, in equilibrium with the orthopyroxene, peridotite, olivine, and garnet, but it's only a compositional difference. And it's very clear that this difference, and we find this difference in the 4 localities: Monastery, Jagerfontein, Premier, and Bullefontein. So it's a very important difference because you can find in a lot of samples. Go to the pattern, and of course we compare the pattern with the rocks we studied just before, the mafic rocks. So, and in fact, some of the trace element pattern of the group 1 clinopyroxene from garnet lerzolite, they show similarity with the peak clinopyroxene. And especially you see this one with this kind of slope, and they have the same kind of anomaly. Sometimes you have difference between, of course, the difference in trace element is also linked to your mineralogy. Peak is just, remember, if phlogopite, ilmenite, clinopyroxene, you have also garnet in the lerzolite. And some of the elements, you have phlogopite, it depends, you know, you have some exchange between some trace elements. But what is very interesting is this. Some of our clinopyroxene are the same than the peak clinopyroxene. And all of them display similarities. For the maride, we compare, it's even clearer. For the second type of clinopyroxene, they have exactly the same pattern. Same anomaly, still the same kind of diagram, normalization to primitive mantle. And it's clear, same clinopyroxene in kind of magmatic rocks linked to kimberlite, and the clinopyroxene we have inside our garnet larzolite. So we come to the discussion. It's clear we have evidence, I think it's clear for you also, of metasomatism of this garnet larzolite. We have occurrence of phlogopite, so modal metasomatism. We have seen, I didn't show you today, but we have also some what we call sinusoidal rare earth element pattern from the garnet, in the garnet, and this is a typical imprint of critic metasomatism. You know, a typical garnet, let's see, I don't want to draw, but you know, if you have a diagram, maybe I can come back to a diagram like this. A pattern of garnet is typically you have high heavy rare earth element content, and you go like this. Okay? What we call sinusoidal is we have a slope like this, you know, and this slope is not a typical pattern of garnet. It's typical of chemical rearrangement of chemical reaction of the garnet. So it's not very important, but even the garnet show evidence of critic metasomatism. Clinopyroxene, I just show you rich in sodium and chromium. Remember, evidence of metasomatism. You can explain these two enrichments by partial melting. And they have also trace element pattern almost similar to those of clinopyroxene of peak rocks, group 1, married rocks, group 2, which are product of the crystallization of melt and mantle depth. The clinopyroxene occurring in both groups of garnet larzolite have crystallized directly from metasomatic melt and are not primary feature of these rocks. Okay? Nature of the metasomatic agent and magmatic agent, trace element characteristic of clinopyroxene suggest that the melt responsible for the modal metasomatism of the group 1 and group 2 garnet larzolite have similarities with the melt responsible for the formation of the peak and married rocks, respectively. Therefore, the metasomatic melt are also high alkaline mafic silicate melt and probably kimberlite. A genetic link has also been proposed between the peak and the group 1 kimberlite, and between the married rocks and the group 2 kimberlite. Such links do allow the formulation of the hypothesis of a genetic relationship between the two mantle metasomatic agents affecting the garnet larzolite, the perilithic mantle from the Caval craton, and the two groups of kimberlitic magma. This is what the main conclusion of the paper we did at that time. Just quickly, I'm talking too much, in fact, no. We have still some study on the way, and especially with my friend, Professor David Bell. He's now working in Port Elizabeth University. He's doing a lot of teaching and to develop the country also, you know, and he has not too much time for research, but we try to go ahead. We want to do some study of the crystal, you know, the study of the crystal geology and geochronology of Western Caval craton have led to the proposal for a collisional erosion. It's just to give you the geological framework at around 3 gigayears, suturing pre-existing continental domain of the eastern and western craton. In fact, in the Caval craton, you have two cratons, with different characteristics. The crystal studies are supported by mantle study that recognize the formation of diamond at this time in subducting oceanic lithosphere, and the most recent interpretation of kimberlite peritic xenolith from the Caval is a convergent margin context. Okay? So this is the framework. To go further with our study, we have carefully selected in the Kimberley area mantle xenolith non-affected by the kimberlitic metasomatic processes. You know, all I showed you before, it was also to allow us to distinguish the rocks. It is a bit similar to people working on eclogite xenolith at this time. We have two main types of eclogite xenolith. We have one type is well affected by metasomatized, and the second type is not affected. So if people they want to have an idea of the protolith of eclogite, they have to select the pristine one and to forget the metasomatic one. This is why also we did the study before. It was to be able to distinguish which garnet larzolite were metasomatized by kimberlite. Because if we want to have information about the history before the kimberlitic time, we need to forget this xenolith and to focus on the. And this is why we are looking for mostly peridotite, non-affected by the kimberlite metasomatic process, and showing evidence of a different type of metasomatic assemblage. If we can have a look at the metasomatism before the kimberlite. And in fact, we have coarse-grained phlogopite-bearing garnet websterite, garnet orthopyroxenite, somewhere the peroxidite mineral occur with phlogopite in some vein patches within refractory garnet arsborgite. So here we are talking about arsborgite in Mantle Xenoliths in kimberlite, so no clinopyroxene. Probably these rocks are never interact with kimberlite. So let's go. It's just a preliminary study on the way. So in fact, we mostly work with a microscope. And in fact, we find already two new groups of peridotite. We have ultra-refractory garnet and chromite-bearing arsborgite and dunite. So no interaction with kimberlite. They are probably all the melt residue. Three of these contain diamond. And in this area, there were no previously found of this kind of diamond in kimberlite. This is the first time. Dave did the job. He found, I will show you a picture, directly diamond inside the peridotite, and it was the first time in kimberlite. He discovered also patches on vein of mica-bearing orthopyroxenate-rich peridotite, orthopyroxenate and garnet websterite, and these are probably product of periodic reaction with melt and fluid, metasomatism, but not linked to kimberlite, because we believe they represent ancient processes. Dunite, they didn't look so beautiful than the younger one. Remember the dunite from Kerguelen? Here it's a bit dark, but it's because they are very serpentinized, and you have only relics of olivine. So difficult to analyze. Probably, for dunite, just to remember, there is three main type of hypothesis. High residue of melting, product of interaction, or cumulates from magma. Now, a lot of people are thinking the residue hypothesis is not working anymore because you need a too high degree of melting. And they play between, in some place, like layered magmatic intrusion, we have evidence, we have pure cumulates of olivine, they are dunite. And I show you in Kerguelen, for example, we have also evidence of interaction, metasomatic interaction in some dunite. But this one, with the Dev, we think that they are pure residue of melting. Because in the Archean time, you have a higher temperature and probably higher degree of melting, and probably you were able to do pure residue. But we have to demonstrate this, and as I told you before, to analyze even in situ is difficult. Maybe separate some olivine, but we have a lot of serpentinite. But so we will see what we can do with this. But remember, we have also dunite in the kimberlitic xenolith, the diamond here. It's a diamond within an arsborgite. Nice garnet, a lot of olivine, and this nice diamond in place occurring inside the arsborgite. It was the first time we discovered this in kimberlite. And it's a little bit difficult to see, but here you can see, here you have a garnet, typical garnet arsborgite. And if you go to the top here, you can see you have only orthopyroxene, garnet, and I will show you another, and in some place, phlogopite. So you have evidence of a vein here. And if I go to this kind of picture made with the scanned electron microscope, you see here you have the part with olivine, let's say the arsborgite, with garnet, and here all of these are orthopyroxene. So we have probably a very old vein. As we have enrichment in garnet, because we are more garnet than in arsborgite, and orthopyroxene, it's probably not a kimberlitic metasomatism. So we will explore this one in detail. And we did the first analysis, and we start with phlogopite. And look, just not to be complicated, barium versus titanium. Here we have all we think are the kimberlitic signature in phlogopite, in situ, with laser. There are almost no barium inside and a lot of titanium. They occur in the maride, in the glimmerite, in some of This one are just some peridotite rich in phlogopite or amphibole. And here, this is a new sample we selected. The one with the vein orthoperoxide is this one. And there is some other garnet arsborgite. And always these big phlogopite are depleted in titanium and very enriched in barium. So we are sure that we have an indication of a different, very different metasomatic event, and now we will go further for the study. And for Dev, it's probably this is a Kimberlite, and this one is a subduction-free signature, but we have to test this. And just to finish, Dev found, I think, this kind of texture in some xenoliths. You know, we have carbonate, magnetite and dolomite, pseudomorph. No, you know this kind of texture. No, if you analyze this kind of texture, you know, this kind of inclusion, they are made of serpentinite, brucite, and calcite. But for Dev, probably it was only because before they were mantle carbonate, and probably associated with metasomatism. And he called this carbonate pseudomorph. You know, sometimes it's big, sometimes it's more than 1 millimeter. Not easy to study because they are transformed, of course. And he thinks that we have evidence of primary mantle carbonate in the cratonic mantle. This is the first time also we discover this kind of stuff. And he said, in fact, we have an hydrothermal alteration in kimberlite, making disappear your mantle carbonate, like the magnesite, you know, plus water, give this kind of brucite and serpentinite. And just for the fun, he started to. The first test we did, he said, do we have this feature in a lot of samples? And in fact, you know, more than 40 they have almost nothing, not of this inclusion. But, you know, it's not 1 or 2 samples. You know, we have several samples with sometimes close to 1% of the modal composition is this inclusion. So they are not they are a rare feature, but they have probably importance to understand, of course, the cycle of carbonate and CO2 within the cratonic mantle. So the question we have, are these metasomatic events related to slab-derived melter fluid, of course, linked to the collisional erosion at 2.9? We actually test the proposal that the reaction between slab-derived melter fluid and overlying mantle has modified the Archean lithosphere and can explain maybe some chemical feature of the continental crust. This is what we have in mind. We also test models that link some Archean diamond formation to this process and anticipate that our study will shed light on the relationship between Archean subduction and carbonate storage in the mantle lithosphere. Finally, we explore the potential impact of these processes on the physical character of the mantle lithospheric roots. You know that the craton have roots. It's a mantle. The lithospheric mantle is going down to, let's say, between 200 and sometimes people think 300, 350 kilometer depth. In a normal phanerozoic lithosphere, the normal thickness is 100 kilometers. Okay, this is why we have the name of roots. It's a So I think it's finished. Yeah, it's just to show you that we are still working. You know, you finish something as a scientist, you publish, and after you go ahead because you have new sample and say, okay, no, we know the kimberlitic signature, so we go to the past. If you have questions, 1 hour, just 1 hour, I am good. So yes, what is very important, I insist on this, the lithospheric mantle is a very important part of the Earth for history and especially history of magma melt. You see, all these metasomatic are because you have melt, fluid going everywhere inside the lithospheric mantle, changing the composition, the mineralogy. So you will have some big after result. When you will put this mantle down, resack this mantle, you can change the composition. So it's not a very inert part of the world, of the Earth. It's living also. It's living with magma, eruption, diamond or not diamond. So we go back to isotopes. You put your computer? So tomorrow I will move from metasomatic processes because you start to be to talk to you about the evolution of the subcontinental mantle lithosphere with PT estimate and with people like people from GEMOG. They propose that the composition of the mantle evolved from Archean time to now and this kind of stuff. Okay. Okay. Okay.
Okay. Maybe you need a break for your brain. It's a lot of information at once. I will try to go slowly. Okay. So yesterday I stopped after telling you about two isotopic systems, the neodymium strontium, neodymium samarium, samarium neodymium, and the rubidium strontium geochronometer. So today I must present to you the lead isotopic system. First, because this is the oldest, in fact. This is the first one which have been used to date geological samples. Okay, the first ages, uranium lead ages have been done in the beginning of the 20th century. even before they know about isotopes. Okay. Of course, the age were completely wrong because they missed totally the physics, the isotopes first, and they missed totally the good, accurate value of the disintegration constant of the uranium. But it was the glorious time of physics, you know, with the discovery of radioactivity, etc., etc. So they tried to apply this to everything, and it was a good idea, in fact, to date the Earth. But the problem, it was just the beginning, so the data they had was not that good. So first, lead, because it's one of the major dating system for the Earth, and it was the first. And second, because it's also extensively used for tracing the magmatic process, even if it's very complicated to interpret, much more than the samarium neodymium and rubidium strontium system. But this is not something I'm going to tell you today. Today we are going to take about dating. So I will just present the uranium-lead system for dating and how it was used to date the Earth. Okay, so some history of geochronometry. So you know these slides. I presented to you 2 days ago. This is the periodic table of the elements. You have uranium, which is an actinide, okay, decay into lead, which is a metal. And if you remember yesterday what I told you, the elements in a crystal are in a very specific place according to their chemical affinity. So uranium and lead doesn't have the same chemical affinity. Okay, so first problem. Second problem, but it's not a problem. This is what we know. The second problem is they don't behave the same way during the magmatic process. You have a melt and a peridotite. The quantity of uranium going into the melt and the quantity of lead going into the melt during the magmatic process is not the same. Uranium is more incompatible, means it loves the melt more than lead. Okay, so during formation of the crust, the continental crust, globally, average, you have more uranium. In fact, you have less because this is a quantity, but you have more uranium lead in the crust than you have in the residual mantle. The uranium lead ratio will be higher, average, in the crust than in the residual mantle. That's the basic. But now let's switch to dating. For dating, this is the opposite. Uranium lead is very, very powerful. And for one unique reason. Because you have two isotopes of the same element that gives two isotopes of the same element, okay, with different half-life. So means if you are measuring lead, you will have information about some ages given not only by one radioactive element, but two, and for the same elements. And this is the tricky part of the lead dating system, is you can play with the isotopic ratio of lead to date, like for a regular, normal isochron diagram, like the one I showed you yesterday, okay, like a straight line. You can play with one. You can play with the other one of the uranium. There is also a third one. This is a disintegration of lead coming from thorium to 32, but thorium is not the same element, okay? This is like you are dealing with samarium neodymium. Of course, there is lead, so there is a link. But you can also play with the isotopic ratio of the father of uranium, okay? Because these two elements are not decaying at the same speed, for example, uranium-235 was much more abundant at the beginning of the of the Earth than now. Why? Because it disappears faster. Okay? So you can measure now the ratio. We know the ratio on the Earth of these two uranium. Okay? The ratio between 238 and 235. We know we can measure it, but we can also estimate it in the past thanks to this disintegration constant. And at the opposite, you can also play directly with the ratio of their daughter, okay, without using the stable lead isotopes. And this is typically the force of the uranium-lead dating system. If you have minerals on the Earth that doesn't have this, the initial lead, they don't trap lead, they don't like lead, they take only uranium, then you will have a direct relation between the radiogenic lead and the uranium. And if you are a little bit mathematician, you realize that dividing this equation by this one, then you will end with the ratio of the uranium, which is perfectly known, and you will end with the ratio of radiogenic isotopes that you can measure. And this is the base of the dating with the uranium-lead isotopic system. You have very easy, measurable data that you can obtain. Very easy. Measuring the uranium is very easy. Measuring lead is very easy. And you can even measure uranium on lead, okay, directly on the mass spectrometer. Of course, this is beautiful, and this is exactly what our physicists think in the beginning of the 20th century, when they realized that the property of this system, they say, wow, this is cool, uranium decay in lead, then we can measure uranium on lead. At the beginning, they didn't know about isotopes, so they just measure the uranium lead. We can measure uranium on lead, and it will give us directly the age. But what they didn't know is this, the disintegration chain. The problem with lead is not directly an atom on uranium changing into lead. You have plenty of daughter isotopes within the disintegration chain. And if you multiply, and all these isotopes are linked each other by a nuclear decay, a nuclear reaction. What is a nuclear reaction? This is a production of the particle or ray and energy. And crystals, minerals, don't like that you are producing energy when they are crystallized. You know, if you are producing energy in the minerals, it tends to be damaged. And if a mineral is damaged, you have the probability to lose a chemical compound. Not not lead, maybe, but also all this product. If you lose, this is what I explained to you 2 days ago, if you lose one atom here, you miss one atom at the end. And then if you are measuring your uranium-lead ratio in your lab, if you miss one atom, then you have an error on the age. Okay? So after they realized that, the physicists first, they decide to find a way, graphically, because it's a complicated system, they decide to find a way to plot the data they have so that they can see if there was some loss during the time where there was this disintegration chain. So, so just a reminder of the fundamental equation. So what they first realized is, okay, we need some, as I said before, we need some minerals in the Earth that does not trap lead when they form. So we are looking for minerals in all the magmatic system which were able to trap uranium but not lead. Okay, so that you get rid about the correction and this fancy that we discussed yesterday, initial isotopic composition. There are some minerals like this, typically the zircons, monazite and sphene, And this is why when you read paper and you read textbooks, you see dating on zircon dating, zircon dating all the time, because this is a very resistant mineral to secondary process. So there is less probability that you are losing some daughter products of the disintegration, and also it doesn't have lead when it forms. So you can transform this equation here. If you have no lead, you don't have to measure this ratio. You have only the produced 207 lead that you will find in your zircon after, I don't know, 1 giga-year of the age of your sample, will be directly the produce of the uranium-235 multiplied by this. Okay, you get rid of this, there is no, and you remove the 204. And then you can transform very easily this equation into this. Okay, just a mathematical trick. And then with this simple equation, you can inject the time. Okay, 1, 0.1, etc. in million years, and the equation will give you this, whatever the minerals. It's a theoretical equation. And injecting time in this equation, you can draw a line where all the points at what we called in geochronology concordant, means they give the same age for uranium-235 and uranium-238. This is what we call concordant ages. And this diagram is called the Concordia diagram. So before showing you a complex Concordia diagram, I try to draw you the way it is built. Okay? If no, this one is a mistake. Sorry. Sorry, I just have to check something. Yes. So if you write here 207 lead on 235 uranium, so the convention in geochronology is to put a star when it's only radiogenic lead. It was not lead at the beginning. The only lead you can measure is the one which was produced by uranium. Okay, that's a convention, and you report it as a function of 206 stars lead on 238 uranium. Okay, the two equations that you have here, and you inject time in this 1 million years, 2 million years, etc., 10 million years, you will have a curve like this. Why you have a curve and not a straight line? This is because this one have not the same disintegration constant as this one. Okay, if they had the same disintegration constant, then you will have a line. Okay, and this curve can be graduated in ages, because this is the ages you use to construct it. Like, I don't know, 0.5 giga-year, 1 giga-year, 1.5, 2, 2.5, 3, etc., etc., etc. And then, if you, in the history of Earth, you have, I don't know what, a granite which crystallizes and crystallizes zircon, the zircon will trap uranium, then gently disintegrate whatever the granite, arc, continental related, Archean, Birimian, whatever. You crystallize a zircon with only uranium inside, because here you are dealing, in fact, only with the uranium ratio. Lead is only radiogenic. This is what it is produced in the minerals. Then all the zircon on Earth, if everything was perfect, should fit on this line. So theoretically, you have a zircon, you measure this ratio inside, whatever the zircon, it should be on this line, and you can date immediately your rock. This is the power of the Concordia diagram and of the uranium-lead geochronological system. Of course, nature is not that simple, and you have this problem of disintegration chains that and the problem of this is the zircon sometimes are not on the Concordia diagram. So I will show you on some example what can happen. So this is a theoretical example of what can happen in a Concordia diagram. You crystallize some zircon. So at the beginning, your zircon are here. And they trap uranium in your rock. And during 2.5 gigayears, nothing happened. Stored nicely in a crater somewhere, no metamorphism, nothing. So your zircon will gently move from here. If he made some 207, uranium decay in 206, but all is trapped in your mineral, nothing escaped, so it fit the line, fit the line, fit the line, etc., up to 2.5 gigayears. This is the first stage you have on this diagram. And then, unfortunately, you have some metamorphic events which reheat your rock, and then you have some losses of the daughter isotopes, the lead, during this event. I will not demonstrate why, because it's complicated, but when you have lead loss, they will follow a line and tend to come back to the initial composition, means 0, because normally a zircon should have no lead. So it's a mixture between zircon with lead, zircon with no lead. And this line, sorry, this line here is called a discordia. This is a concordia with concordant edges. This is a discordia with discordant edges. And now, in fact, the rock is not 2.5 gigayears. The rock is older. Though during 1 gigayear more, the system is blocked again and continue to evolve. What happened to this zircon here? They will evolve the same way they were evolved before. They will define their own concordia because there is no thermal event. Sorry. And then you arrive and you sample with your little hammer, your granite, which have 3.5 gigayear, and then what you find, you are measuring the zircon here, and what you are measuring is this here. Surprisingly, you will notice that there still are a line on another discordia, and this discordia with the upper intercept, which will be considered as your crystallization age. And I will not demonstrate why graphically, because the mathematics are very complicated, and I'm not sure I'm able to do it. And the lower intercept will cross the concordia at the age of the metamorphic event. This is complicated to demonstrate because this equation here in the Concordia diagram, this equation cannot be solved directly. Okay, this is iterative equation. Okay, so you cannot solve them directly to demonstrate that you have a straight line. But believe me, some people have done it and have demonstrated that it's normal in that in this case you fall on another discordia, and a lot of study you will find in the literature about zircon dating. Either they are plotting the data like this, or they will use another type of plotting, which is called the Wasserburg way of plotting. Doesn't matter, I will not enter into the Wasserburg diagram today. It's enough with one, okay? But they will plot, and they will, if the simple is not too complicated, interpret it at a discordant age. Of course, everybody would have loved to have zircon here, huh? And everything concordant, then we have the age, we don't have it to discuss. But sometimes it doesn't happen. There are many, many techniques to try to have zircon. The first is the recognition optically of your zircon, okay, under your microscope. When you separate your zircon, you have science of describing the zircon to check if there have been damage, if there is a core, a rim, etc. I will show you with another example later. But sometimes you have zircon, and this is the only zircon you have, so you measure them, and you find discordant ages, and you know that if you have other arguments regarding the geodynamic context you are working with, then you can interpret this as the crystallization age of your protholith and the metamorphic age of your protholith. This is the Concordia diagram. Let's show you another example. Of course, I will give you examples that works. Huh? There are many that doesn't, but to learn, it's better to have examples that work. So Kroner, this is an example from a paper from Kroner et al. In 1987. They were working on Sri Lanka metasediments metamorphosed in the granulite facies. And this is what they found. So first I will plot the data, and then we are going to interpret them together. So let me write properly the data. You have 206 to 38, 207 to 35, I can draw the Concordia like this. They have points here. Which goes here, you have 3.5 giga-year. Here you have 1.1 giga-year. And they have point here. And this, of course, this is 0. Then these points have been measured in old rounded zircon. Okay. This zircon gives very concordant ages, and this one. Then you have other type of zircon, but zone. So here it's old zircon cores with new rims. And here in the core you find this one, and in the rims, you find this one. And then you have new irregular zircon. And all the points measured in this irregular zircon plot here. So let me give you some scale about the value. Here you have 20, 10. Here you have 0.6, 0.4, 0.2. So, in my previous example, I told you about how to construct a diagram and how to the point are behaving in a magmatic event, crystallization, and then you have a metamorphic event. But when you are a geochronologist and you're measuring your data with this is a typical ion microprobe data. Okay, so you can really make some spot in the zircon. When you are dealing with this kind of data, you don't know anything about the system. You just end with points in the diagram. And most of the time, this is not points. This is error. You have error ellipse, okay, but we don't care in this case. And then you have this. You have the shape of your zircon, and you have to interpret them. So, what we have in this kind of example? We have metasediments, means that the rock have a detritical origin. Okay, it was not a melt, it was a metasediment. And what you can have in sediments, it's zircon coming from the massif where there was erosion, because they are very resistant to erosion. They can be trapped into the sediment. So when you have a metasediment, you can think maybe in my metasediments, maybe I have zircons. So maybe my old rounded zircons are the generation of sedimentary zircons. They give the age of my rock when my sediments was formed. And then there was some sedimentation, and I have a discordia. So at 1 gigayear, there was a metamorphic event which affect my rock, and then my zircon left some lead. Okay, some are concordant, and the one which were really heated, they left some lead. They fall on this discordia. I found this kind of point in this old rounded zircon, but also in some cores of new zircon. Okay, and then during this metamorphic event, I have generation of a new zircon rim during the metamorphic of my granulitic facies metasediments. Okay, and then because it's granulitic, no, granulitic was later, because in my metasediments, because there was a granulitic facies, even the core which was formed during this metamorphic event then can lose lead again, okay, up to 0. And then you have a generation of new irregular zircon which fit on this line, and you have also the rim of this one which experience some lead loss which can fit on this line. So on this kind of diagram, when you have a very good example like this, and you have a good zircon typology, you can tell very complex story, okay, only using the Concordia diagram. This is a very nice example. Most of the time it's more complicated like this, and in fact, apart from this kind of study, people like to date and to have really the crystallization age of the of the magma, or in this case, the detritical age. So that's the basic of the geochronology in terms of uranium lead. But before, I will not speak about tracing of magmatic system today, but I will tell you how now this kind of data have been used to date our planet. So this is more historically used with the uranium lead system, and you will see that it's different from the zircon and the Concordia diagram used with zircon, because we have no zircon which can trace the origin of the solar system. Okay, zircon was formed later in this process, but there was also a way to use the uranium lead system to date the Earth. So a little bit of history first. Because it's interesting to see how the people have the idea to use this system to date the Earth. So the age of the Earth is a very old question, okay? It starts to be the age of the Earth is minus 4,000 years before Christ, okay? And then people discover that maybe it can be older. But before before radiochronology, it was difficult to have an idea about the scale. The first age, in fact, really to speak about history, was calculated by physicists imagining that they were comparing the Earth to a big sphere of iron, and they were calculating the time you need to freeze an iron sphere, and they were transferring this calculation to the Earth. It was not that accurate, so it switched between some 75 or no, 200,000 years to some million years. Calculation was wrong. But in 1904, Rutherford discovered that alpha particles are released in radioactive decay, and then could be trapped in rocks. So he measured, there was some measure of 40 million years, so not the age of the Earth, but at the beginning in 40 million years. Then in 1905, they realized that lead is the stable daughter isotope of uranium, and during using this kind of method, they start to date some rocks, but they did not know anything about the isotopes. So the age were wrong, but the idea was correct. Okay? After, and this is one of the diagrams I'm going to present you, the big jump was done by Arthur Holmes, and because first they knew that thanks to physicists, that there was some isotopes, both in uranium and lead, and they apply it to the uranium lead dating. The first calculation of Holmes was wrong, okay, because they had not a good idea about the constants of disintegration of uranium and lead, and before he died, the calculation of the age of the Earth made by Holmes was around 3.35 billion years. Okay, the first modern and good, we hope it's good, calculation of the age of the Earth was done by Patterson. I will show you one of his results. It used the Holm-Uterman model to date the meteorites, and also this diagram was also used to date some Earth sample, and I will show you what kind of sample he died he died recently, in fact, in 95. So let me show you what is my next diagram. Yes. So conversely to what is used in the Concordia diagram, today the Earth, as I told you, we don't have zircons. So it's a problem. We don't have systems which have been formed at the beginning of the solar system that are still there and that does not enclose lead in their crystal matrix. So we have to use the equation in a different way. We have to, principally, the idea is to imagine what can be we need an initial isotopic composition of the solar system. That's difficult to have an idea. So we need to find something which can give us the initial isotopic composition of the solar system. And if we have this initial isotopic composition, then we can play with the equation in order to calculate the age of the Earth. And this is what is written in this equation. So we come back to the fundamental equation, and we want to know this. And I forget about thorium. And we want to simplify the equation so that we don't have to know the uranium isotopic composition at the beginning of the solar system, but only the lead isotopic composition at the beginning of the solar system. So it's simple. You take these two equations, okay? Either we're on lead 204 or directly like this. You divide one by the other, like this, okay? And then you subtract the initial isotopic composition that somebody has to give you. This ratio, we know. This is the present ratio. So it's the opposite, the 238 on 235 is 1.37.88. And what we know also, so I have to write to you some basic constant for lead that you should know. So the disintegration constant I gave you, but by chance we found in the US they found an iron meteorite, so belonging to the beginning of the solar system, which doesn't have any uranium inside. So when you have an iron meteorite was formed at the beginning of the solar system, and this rock did not enclose any uranium, you have the opposite to zircon. Zircon encloses only uranium and no lead, and here you have a rock, old, which have no uranium and lead. So if you measure the isotopic composition of these rocks, maybe this is the initial isotopic composition of the solar system. So this rock is known as the Canyon Diablo troilite. And it was it was used before by Patterson, for example, but it was precisely dated to be sure that it is not the core of a planet, and it's really an iron meteorite from the beginning of the solar system. It was dated by Tatsumoto. Et al. And this is the date which is used by everybody in 1973, which gives you an age of 0.77 giga-year. So this Canyon Diablo troilite have an isotopic composition. Oh, sorry, this is the way I 206 lead, 204 lead equal 9.307, 207 lead, 204 lead equal 10.204, and 208 lead on 204 lead equal 29 dot this is the least radiogenic, lead radiogenic isotope ever measured in a sample, since we know how to measure the isotopic composition. And because it's a meteorite, it's considered to be the first, the isotopic composition at the beginning of the solar system. So this meteorite is extensively used to date the Earth and to be a reference for this kind of dating. Of course, there are other that can have been measured, other stony meteorites that have been measured, which share the same isotopic composition, but this one is a reference. There are other notation in uranium-lead systematics that I need to give you because I will use them later. We define the ratio called mu as the 238 uranium on 204 lead. This is mu is an idea to have an idea about the relative enrichment of the source of your rock regarding uranium and lead. And you have another kappa, which is the ratio 232 thorium on 238 uranium. This is some basic constant that you should know regarding lead. So how Holmes-Uterman, so Holmes they did this dating. He used a specific ore that you find on the Earth, which are like the Kenyan Diablo meteorite. It's the galena. Galena are a lead ore, okay, with only lead and no uranium. So it's a little bit like the meteorite, okay, the Kenyan Diablo meteorite, but in Earth system. And when Holmes developed his method of the Earth, they did not know about the plate tectonics. They did not know about the crust, the mantle, etc. All these geodynamics that you know now, they believed that Earth was a global system, okay, and it was relatively homogeneous. So they say, at the beginning, we have the Kenyan Diablo. It's not too low here. Maybe I can. You wrote already what I wrote here, so I will wipe out. Then they plot a diagram, which is what we call the common lead diagram. It's not lead on uranium, but it's lead isotopic ratio. Here you have the 206, 204, and here you have the 207 lead, 204 lead. Here I have my Kenyan Diablo troilite, the beginning of the solar system. Then everything from the Earth. All samples of Earth have their different uranium-lead ratio, but uranium produced is the decay here, and uranium is also decay here. There I measure a galena. I take a galena, which is found in, I don't know, in a mine, which have a certain age. I don't have any idea. It is there. If the Earth is the uniform reservoir, my galena fossilized the lead isotopic composition at the time it's formed. Okay? it's formed at 1 gigayear or 2 gigayear, then it traps the lead produced by the uranium which was around, and because uranium is there, it's there, there is a unique composition. Then I take another galena for somewhere else in another geological time. I measure the lead isotopic composition. It's there. I don't have any idea of the age. Again, I sample the galena on Earth, and I measure the composition. And this galena, if my equations are correct, fit on a line, a curve, again a curve, I'm sorry, it's not a line, because there is two exponential of different lambda on the both on the numerator and the denominator. And if I have a computer, or if I'm a very good mathematician, because it's not cannot be solved directly by linear algebra, I can fit the line and then solve the equation. And then if I can solve the equation, I can define the ages. So maybe this is 1 gigayear, 1.5, 2.5, 3.5, etc., etc. And if I'm able to draw these different isochrones on this line, then I'm able to calculate the age of the Earth, which is given by the curvation of this theoretical line. This is the Holmes-Utermann model. The Holmes-Utermann model is a fitting of the galena that give you all the parameters of this equation, which finally help you to find the time here. Okay? So the problem with the Holmes-Utermann model is they believe that the Earth is a homogeneous reservoir and the galena are sampling homogeneously the Earth, which is not. Okay? Which is not, because they didn't know about the convection, they didn't know about the melt extraction, they didn't know about the crustal, the continental crust generation, and so they, in fact, at the beginning, it was working. This is why they found this age of 3-point-something gigayear. It was working because there are very few data. There are some 3, 2, 1, 2, 3 galena. The first publication was with 1 galena and the Canyon Diablo. 2 points to fit this line here. So the error was big because either the error of the measurement were big, and then the error were big on the calculation of the age. But they refined the model. Finally, they realized they try to define some galena which are not secondary product of alteration of the crust, but much more related to volcanic sediments, so maybe close to the mantle. So they maybe are a good average of the crust of the Earth isotopic composition. But even that gives very bad ages. And finally, the Holmes-Utermann model was abandoned, and there are another guy. So this is another model of Earth that was proposed by Stacey and Kramer in 19. Stacey and Kramer, which is also famous, in 1959, where they proposed that, in fact, this is a two-step evolution. So what is a two-step evolution? Is exactly what I show you 2 days before or yesterday with the samarium neodymium. Before making the continental crust with a certain mu1 ratio, And here you don't form any galena because there is no crust. And after this mu1, you have, I need the figure because I want to make the curve correct. There is another evolution. You at 3.5 gigayear here. And there is a mu2, another evolution, mu2, where all the galena, what they call the conformable galena, fit better and which give a better age for the Earth. And this is the Stasek-Kramer model. Okay, so the Stasek-Kramer model, even if it's a model, it's more consistent with what we know about the dynamic of the Earth, means fabrication, construction of the continental crust, and nothing before. But finally, the final justification of using these late isotopes to calculate the age of the Earth was first demonstrated by the guy I told you before, which is Claire Patterson. And Claire Patterson, so this is the same diagram I show you there. And Claire Patterson used another approach, which is totally independent from this story of galena. He used the meteorite to calculate the age of the solar system, believing that the solar system and the Earth are the same age. And he measured the lead isotopic composition of different meteorites. So here this is only 2, because this is the first diagram published, but then it was refined especially by Tatsumoto, the guy also I told you before, and there are many meteorites that can fit on this diagram. And on this diagram, in fact, if you have a meteorite with no uranium, which will be there, if you have a meteorite with a little bit of uranium, its curve will be there. So it's not this case, will be there. Then it will end here today. If you have another meteorite with more uranium, it will be there, it will be there, etc., etc. And when you're measuring, so Tatsumoto paper, there are many meteorites which are perfectly fitting on this line. Of course, you have to consider that this one is perfectly the composition of the Earth at the beginning. And then if all the meteorites are fitting on this line, then you can have directly the age of the Earth. In fact, you have to consider that they are all the same age, and if they are fitting, you can come back on the age using the equation I present you before. And what Claire Patterson did also in his paper is he took the isotopic composition of some average oceanic sediments, saying this is the average isotopic composition of the Earth. And he plotted on this line, on this diagram, and this average modern ocean sediment are fitting with all the meteorites from the solar system. So that was an indirect evidence that the Earth had the same age as the meteorite. Because the age, if you consider that the modern ocean sediment have a certain mu, which is the average mu of the Earth, then if they are fitting here, if now they are the isotopic composition, they are fitting on the 4.757 billion year, then the Earth have the same origin. This is an evidence. There are other, okay, especially the distribution of the element, but this is one of the evidence that, and this is up to now the best estimate of the age of the Earth. It was refined by Tatsumoto also because Tatsumoto have access to a better physical knowledge about the constants of disintegration, and that at this time Claire Patterson did not have. This is why he found 4.15 0.55 and 0.457. Okay, it was a problem between the, it's very difficult to measure the constants of disintegration thanks to nuclear physics. They don't do only bombs; they also do some good stuff, and so they can calculate, counting number of helium produced, in reactors by the disintegration of uranium. They can count the particle produced and come back to the constant of disintegration. And that's it for today. So we finish with lead. So you have seen, I will not go into lutetium hafnium systematics because it's almost the same than samarium neodymium. And then you have an overview of the three main isotopic systems which are used in Earth science for dating, but also for tracing. I will tell you a little bit when we are going to talk about the subcontinental lithosphere, about osmium. Then I will give you some detail about the behavior of this system. But in terms of geochronology, that's it. Okay, the Concordia, the way you date the Earth. Okay, you are not going to date the Earth because it's already dated, so it's history of geochronology. Maybe if you go on Mars, maybe you will date Mars, but you have to come back. Huh? I'm not sure you will go to Mars with your mass spectrometer. So, if you have a question about lead or age of the Earth, radioactivity, dinner time. Okay, so everything was clear. Huh? I will not come back on the lead isotopic system when I'm going to use it